your papers at D-band, so everybody else should download that paper and read it after this as well. And Dr. Axo's research interests include RF semiconductor device design, nanofabrication, modeling, characterization, as well as the RF circuit applications of such devices for high power, efficiency, linearity, and low noise. So with that, Emory, the floor is yours.
Thank you, Steve. So can you hear me and can you see my screen?
Absolutely. You sound great.
Okay. So this is Emory Axo joining from the University of California, Santa Barbara, Professor Umesh Mishra's research group. So today I'm going to talk about the demonstration of record 1 watt output power from an N-Polar GaN MISHEMT at 94 gigahertz. And this result was demonstrated with W-band Maury active local system. So I'm going to start my talk by talking about the challenge of obtaining high power at W-band, and then the N-Polar GaN MISHEMT technology for achieving simultaneous high power and efficiency, and some record W-band large signal performance from two-finger N-Polar GaN MISHEMTs. So the challenge of obtaining high power at W-band starts at the transistor level. So today, the traditional state-of-the-art gallium polar GaN transistors give about 2 watts per millimeter at W-band. So for a typical gate periphery of 150 micron device, this corresponds to 300 milliwatts from a single transistor. So to get to a watt or a couple of watts power from at the chip level, we typically need to combine 2 to 10 of these devices at the output stage of the power amplifiers to get even more power at the system and module level. So many of these chips need to be combined. So although the transistors themselves are tiny, the power per transistor has a huge impact on the final system size and weight. So that's why the transistor power is very important because the large scale power combining has diminishing returns and it lowers the total system efficiency. So a device that can give 2x the output power that the standard state-of-the-art gallium polar devices can provide would reduce the final system size and weight substantially by requiring the number of chips, reducing the number of chips required. So as the Mishra group, the solution we offer is the N-Polar GaN technology. Specifically, what I'm showing here is the N-Polar GaN D-precess HEMT structure, which employs a GaN cap, and the gate is recessed through the GaN cap in the structure. And the purpose of the GaN cap is to reduce DC to RF dispersion and enhance the access region conductivity. And we have an all GaN cap and MOCVD silicon nitride gate dielectric in the structure to ensure that the gate leakage is low. And optionally, we have a silicon nitride passivation for further dispersion control beyond what GaN cap itself can offer. And these devices employ MBE regrown M plus GaN ohmic regions for low ohmic contact resistance. And the main and the biggest difference and differentiation from the gallium polar technology is that the two-deck inducing barrier layer is at the back rather than at the top, like in the gallium polar technology. So this back barrier acts as a natural back barrier which confines the two-dimensional electron gas in the channel and reduces the buffer leakage. And at the same time, because this charge-inducing barrier is at the back, not at the top, we can independently tune the charge density in the channel and the distance between the gate metal and the channel. So this means that we can simultaneously tune the current density and the gate aspect ratio, which enables us to achieve devices that can give simultaneous high power and high efficiency. And here I would like to share with you some W-band performance from two-finger devices. And again, this large signal performances were measured with Maury passive local system at 94 gigahertz. And on the left, you're seeing some record PAE results on low-cost sapphire substrate. So we demonstrated 4.4 watts per millimeter with 42% PAE from 2x25 micron devices before passivation. And after passivation, we demonstrated 5.8 watts per millimeter with 38.5% associated PAE. And on silicon carbide substrate, we demonstrated record power densities again. An example of this is 8.85 watts per millimeter from 2x37.5 micron devices with 27% associated PAE. And now I would like to talk about multi-finger, the devices with more than 2 fingers, N-Polar GaN HEMTs for high total cell power. So as I mentioned, N-Polar GaN gives very high power densities, but at the end of the day, what we care about is the total power in watts from a single power cell. So we need to maximize the power per cell by increasing the periphery of these, total gate periphery of these devices. And to do that, we cannot simply increase the finger width of these devices forever, because doing so will increase the gate resistance, which will limit the gain and efficiency. So the typical approach is to increase the number of fingers, which in the CPW wiring environments requires air bridge connections between the source pads. So for this, we developed an air bridge process, and you can see fabricated air bridges on the right. And this process was compatible with delicate T-gate structures. So although air bridges are effective at connecting the sources together, they also introduce additional parasitics, such as air bridge to gate capacitance, air bridge to drain capacitance, and air bridge inductance, which acts as a source inductance for the inner 2 fingers. And to simulate these effects, we used COMSOL and HFSS. Here you're seeing the simulation results for the CGS air and LS air with respect to layout parameters, as well as some air bridge design parameters. And based on this study, we selected some design parameters. And with these design parameters, the expected CGS air bridge was 15 femtofarads per millimeter, and the source inductance associated with the air bridge was 3.2 picohenry. Then using a 2-finger small signal model and using these air bridge parasitics, we were able to simulate the maximum available gain, maximum stable gain versus frequency for different topologies, namely 2x37.5 micron, 4x25 micron, and 4x37.5 micron. As you can see, at 94 gigahertz, 4x37.5 micron device has a lower gain than the other topologies, which shows the importance of choosing the correct gate periphery and number of fingers and finger widths, as well as managing the parasitics of the device. And then we fabricated these devices. On the left, you're seeing a 4x25 micron device, and we measured S parameters of these devices. And from these measured S parameters, we extracted the average parasitics again. And as you can see, these extracted parameters from the measured S parameters agree closely with the COMSOL and HFSS model prediction. After the small signal characterization, we did large signal characterization on a 2 by 37.5 micron device and a 4 by 25 micron device using Maury passive load pull system at 94 gigahertz. And these devices were biased at 20 volt VDSQ and a class AB bias of 0.4 amps per millimeter IDSQ. And basically going from 2 by 37.5 micron to 4 by 25, we were able to maintain the power density of 7 watts per millimeter and maintain the drain efficiency, PAE, and the linear gain. So the 4 by 25 micron device demonstrated 712 milliwatts with 32% PAE. And this power level was the highest output power ever reported from a transistor at W band, and which was published in IEEE MWTL. And now, what if you wanted to obtain even more power at watt level, making a watt level device basically? So demonstration of record 1 watt output power from a single HEMT. So I will first talk about the limitations of the passive load pull at W band in characterizing such devices, and Maury active vector load pull system, and characterization of a large periphery 4 by 37.5 micron device, and Cripps' PA analysis for power and drain efficiency verification. So first, I would like to talk about the limitations of the passive load pull for characterizing large periphery devices. On the left, you're seeing the dashed line. The dashed circle shows the typical matching range of the passive load pull at 94 gigahertz. And also you're seeing the simulated optimum load reflection coefficient at the probe path reference plane for different topologies. As you can see, as we increase the periphery, the amplitude of the required load reflection coefficient increases. So in this example, we cannot properly characterize a 4 by 37.5 micron device using passive load pull because of the limited matching range. And as the Mishra group, to tackle this problem, we acquired an active load pull system from Maury. And the purpose was to, again, overcome the limits of the passive load pull with limited matching range at high frequencies because of the system losses. And on the other hand, the active load pull is capable of synthesizing load reflection coefficient magnitudes as high as unity and enable load matching for large peripheries. So if you are interested in learning more about the system, or if you have more system-related questions, you can read Christopher Clymore's paper, which was presented at RF Tech 2023. So then I would like to talk a little bit about the DC and small signal performance of these big periphery devices before going into the large signal characterization of these devices. So for the DC performance, these devices demonstrated 1.5 amps per millimeter drain current and a very low IG, the gate current of 2.7 nanoamps per millimeter at plus 2 volt VG with peak GM of 427 millisiemens per millimeter. And for the small signal performance, what we're reporting here is the peak Fmax bias condition. So at the peak Fmax bias condition, the Fmax is 242 gigahertz with an associated FT of 118 gigahertz. and the large signal characterization of these devices with Maury active local system at 94 gigahertz. Again, the quiescent bias is 20 volt VDSQ and 0.4 amps per millimeter IDSQ. And this device was able to show 6.7 watts per millimeter, which is 1 watts total output power with an associated 21.4% PE and 2.3 dB compressed gain. And this is again the highest output power reported from a single transistor at W band. And as you can see, the benchmark on the right, to the best knowledge of the authors, there is no gallium polar device with larger than 500 milliwatts total power at W band. But what we demonstrate here basically is more than 2x of the best gallium polar GaN device could ever provide. So then we wanted to verify the active local results with Cripps' PA analysis. For this, we have the load reflection coefficient at the pad reference plane. This is from the measurements optimization. And then we de-embed the drain side pad inductance and capacitance and obtain the load reflection coefficient at the drain reference plane. So using the load reflection coefficient at the drain reference plane, we can calculate the load line resistance. And by placing the load line resistance on the IV plane, as you can see on the left, we can learn the knee parameters, knee voltage and knee current, and maximum voltage and the off current. So using these knee parameters and the off state parameters, we can then do Cripps analysis to predict output power density and drain efficiency. And as you can see, this theoretical prediction closely agrees with the measurement results. And the summary. So we established a design space for multi-finger N-Polar GaN HEMTs in number and width of the fingers, as well as in the average design. And we demonstrated record power performance at W band from a single transistor. So 712 milliwatts with associated 32% PE, which was characterized by a passive local system, and 1 watt with associated 21.4% PE, which was characterized with an active local system. And I also would like to acknowledge our founders from ONR, Dr. Paul Mackey, and from DARPA, Dr. Tom Kager.